Welcome to the world of data structures. In this video, we'll explore what data structures are and why they're so important in computer science. Data structures are the backbone of efficient programming, allowing us to store, organize, and manage data effectively. Whether you're building a simple app or designing complex algorithms, understanding data structures is essential. Throughout this journey, we'll break down the core concepts, look at real-world examples, and see how data structures impact the way computers solve problems. Let's start by defining what a data structure really is and why it matters. Data structure is a specialized format for organizing, processing, retrieving, and storing data. Think of it as a container that holds data in a particular way, making it easier to perform specific operations. For example, a list of names can be stored in an array, while a phone directory might use a tree structure. The choice of data structure can greatly affect the efficiency of your program. In the next scenes, we'll explore different types of data structures and their unique features. Data structures are crucial because they determine how efficiently data can be accessed and modified. Imagine searching for a book in a library. If the books are arranged randomly, it would take ages to find the one you want. But if they're organized alphabetically, the search becomes much faster. Similarly, choosing the right data structure can make your programs run faster and use less memory. Next, let's look at some common types of data structures you'll encounter. There are many types of data structures, each suited for different tasks. The most basic ones include arrays, linked lists, stacks, and queues. More advanced structures like trees, graphs, and hash tables are used for complex data relationships and fast lookups. Understanding the strengths and weaknesses of each type helps you choose the best one for your needs. In the following scenes, we'll dive deeper into each of these data structures. Arrays are one of the simplest and most commonly used data structures. They store elements in a fixed size sequential order, making it easy to access any element using its index. Arrays are great for situations where you need fast access to data and know the number of elements in advance. However, inserting or deleting elements can be slow, especially if you need to shift many items. Next, let's see how linked lists offer more flexibility. Linked lists are dynamic data structures where each element, called a node, contains data and a reference to the next node. This allows for efficient insertion and deletion of elements as you only need to update a few references. Linked lists are ideal when the number of elements can change frequently. However, accessing elements by index is slower compared to arrays. Let's move on to stacks and see how they work. Stack is a linear data structure that follows the last in, first out LIFO principle. Imagine a stack of plates. You add new plates on top and remove the top plate first. Stacks are used in programming for tasks like undo operations, function calls, and expression evaluation. They're simple to implement and very efficient for these specific tasks. Next, we'll look at queues and how they differ from stacks. Queues are another linear data structure, but they follow the first in, first out FIFO principle. Think of a line at a ticket counter. The first person in line is served first. Queues are used in scenarios like task scheduling, buffering, and managing resources. They ensure that tasks are processed in the order they arrive. Now let's explore more complex structures like trees. Trees are hierarchical data structures made up of nodes, with a single root node and branches leading to child nodes. They're perfect for representing relationships like family trees, file systems, or organizational charts. Trees allow for efficient searching, insertion, and deletion. There are many types of trees such as binary trees and AVL trees, each with unique properties. Next, we'll see how graphs expand on these ideas. Graphs are versatile data structures that consist of nodes, or vertices connected by edges. Unlike trees, graphs can have complex relationships including cycles and multiple connections between nodes. They're used to model networks like social media, transportation systems, and the internet. Graphs can be directed or undirected and weighted or unweighted depending on the application. Let's now look at hash tables and their unique advantages. Hash tables are powerful data structures that use a hash function to map keys to values. This allows for extremely fast data retrieval, making them ideal for tasks like database indexing and caching. Hash tables handle collisions using techniques like chaining or open addressing. They're widely used in programming for their speed and efficiency. Next, let's discuss how to choose the right data structure for your needs. Selecting the right data structure depends on the problem you're trying to solve. Consider factors like the type of data, the operations you need to perform, and the efficiency required. For example, if you need fast lookups, a hash table might be best. If you need to maintain order, an array or linked list could be more suitable. Understanding the trade-offs of each structure is key to writing efficient code. Next, we'll look at how data structures impact algorithms. Data structures and algorithms go hand in hand. The choice of data structure can make or break the performance of an algorithm. For example, searching for an item in an unsorted array takes longer than searching in a balanced tree. Efficient algorithms rely on the right data structures to minimize time and space complexity. In the next scenes, we'll see some practical examples of how data structures are used in real-world applications. Social networks like Facebook and Twitter use graphs to represent connections between users. Each user is a node, and friendships or follows are edges connecting them. This structure allows for efficient searching, recommendations, and analysis of relationships. By using graphs, social networks can quickly find mutual friends, suggest new connections, and analyze user communities. Next, let's see how search engines use data structure. Search engines use hash tables and trees to index billions of web pages. When you enter a query, the search engine quickly looks up relevant pages using these data structures. Hash tables provide fast access to keywords, while trees help organize and rank results. This combination ensures that you get accurate and speedy search results. Now let's look at how file systems rely on data structure. Most computer file systems use tree structures to organize files and folders. The root directory branches out to subfolders and files, making it easy to navigate and manage data. Trees allow for quick searches, efficient storage, and logical organization. This structure is why you can easily find and manage files on your computer. Next, let's see how databases use data structures for performance. Databases use a variety of data structures, including B-trees and hash tables, to index and retrieve data efficiently. Indexing allows databases to quickly locate records without scanning the entire dataset. This is crucial for large-scale applications where speed and accuracy are essential. By choosing the right data structure, databases can handle millions of queries per second. Let's now discuss how data structures are used in gaming. Video games use data structures to manage everything from player inventories to game worlds. Arrays might store player stats, while graphs represent maps and connections between locations. Efficient data structures ensure smooth gameplay, quick loading times, and responsive controls. By optimizing data storage and retrieval, games can handle complex worlds and large numbers of players. Next, let's look at how data structures help in artificial intelligence. Artificial intelligence relies on data structures to process and analyze large datasets. Trees and graphs are used in decision-making algorithms, while hash tables help with fast lookups. Efficient data structures enable AI systems to learn, adapt, and make predictions quickly. Whether it's recognizing images or understanding language, the right data structure makes all the difference. Now, let's discuss the importance of time and space complexity. Evaluating data structures, it's important to consider both time and space complexity. Time complexity measures how fast operations can be performed, while space complexity looks at how much memory is used. The goal is to find a balance between speed and resource usage. For example, arrays offer fast access but can waste space if not fully used. Understanding these trade-offs helps you make better design choices. Next, let's look at how data structures evolve over time. Data structures have evolved alongside advances in computing. Early computers used simple arrays and linked lists, but as problems grew more complex, new structures like trees, graphs, and hash tables were developed. Today, data structures continue to evolve to meet the demands of big data, cloud computing, and artificial intelligence. Staying updated with the latest developments is key for any programmer. Next, let's discuss abstract data type. Abstract data type, or ADT, defines a data structure purely by its behavior from the point of view of a user, rather than its implementation. For example, a stack ADT specifies push and pop operations but doesn't dictate how they're implemented. This abstraction allows programmers to focus on what a structure does, not how it works internally. Next, we'll see how ADTs relate to concrete data structures. While an ADT defines the operations and behavior, a data structure is the actual implementation. For instance, a QADT can be implemented using arrays or linked lists. This separation of interface and implementation makes code more flexible and easier to maintain. By understanding both ADTs and data structures, you can design better software. Next, let's look at how data structures are represented in code. Data structures are represented in code using variables, classes, and objects. For example, an array can be declared as a simple variable, while a linked list might use a class with nodes and pointers. Modern programming languages provide built-in support for many data structures, making it easier to implement them. Understanding how to code these structures is essential for any developer. Next, let's discuss the importance of data structure operation. Every data structure supports a set of basic operations, such as insertion, deletion, searching, and traversal. The efficiency of these operations depends on the structure used. For example, searching in a hash table is much faster than in a linked list. Knowing which operations are most important for your application helps you choose the right data structure. Next, let's look at how data structures handle memory management. Efficient memory management is a key consideration when working with data structures. Some structures, like arrays, allocate memory in advance, while others, like linked lists, allocate memory as needed. Poor memory management can lead to wasted resources or even program crashes. Understanding how each data structure uses memory helps you write more reliable and efficient code. Next, let's discuss dynamic and static data structure. Data structures can be dynamic or static. Static structures like arrays have a fixed size, while dynamic structures like linked lists can grow or shrink as needed. Dynamic structures are more flexible but may require more complex memory management. Choosing between static and dynamic depends on your application's requirements. Next, let's look at linear and nonlinear data structures. Linear data structures like arrays, stacks, and queues arrange data in a sequential order. Nonlinear structures like trees and graphs organize data in a hierarchical or interconnected way. The choice between linear and nonlinear depends on the relationships within your data. For example, hierarchical data is best represented with trees. Next, let's discuss the importance of data structure selection in software design. Selecting the right data structure is a critical part of software design. The wrong choice can lead to slow performance and difficult maintenance. By analyzing the requirements and expected operations, you can make informed decisions. Good design leads to scalable, efficient, and maintainable software. Next, let's look at some common mistakes when working with data structures. Some common mistakes include using the wrong data structure for a task, not considering time and space complexity, and poor memory management. These errors can lead to slow, inefficient, or buggy programs. Always analyze your needs and test different structures to find the best fit. Next, let's discuss how to practice and master data structures. The best way to master data structures is through practice. Work on coding exercises, solve real-world problems, and participate in programming competitions. By applying your knowledge, you'll gain a deeper understanding and become more confident in choosing and implementing data structures. Next, let's look at resources for learning more about data structures. There are many resources available for learning data structures, including textbooks, online courses, and tutorials. Interactive platforms like LeetCode and HackerRank offer hands-on practice. Reading code written by others and contributing to open-source projects can also help you improve. Next, let's discuss the role of data structures in interviews. Data structures are a key topic in technical interviews. Employers want to see that you can choose and implement the right structure for a given problem. Practicing common interview questions and understanding the underlying concepts will help you perform better. Next, let's look at how data structures are used in different programming languages. Different programming languages offer different built-in data structures. For example, Python has lists and dictionaries, while Java offers arrays, lists, and hash maps. Understanding the available options in your language of choice helps you write better code. Next, let's discuss the future of data structures. As technology evolves, so do data structures. New challenges in big data, artificial intelligence, and cloud computing drive the development of innovative structures. Staying updated with the latest trends ensures you remain competitive in the tech industry. Next, let's summarize what we've learned about data structures. We've covered the definition, types, and importance of data structures, as well as their real-world applications and best practices. Remember, the right data structure can make your programs faster, more efficient, and easier to maintain. Keep practicing and exploring new structures to deepen your understanding. Next, let's look at some tips for mastering data structures. Master data structures, focus on understanding the core concepts, practice regularly, and study real-world examples. Don't just memorize definitions, work on implementing and using data structures in different scenarios. Over time, you'll develop an intuition for choosing the right structure for any problem. Next, let's discuss the importance of continuous learning. Field of computer science is always evolving, and so are data structures. Make it a habit to learn about new structures, algorithms, and best practices. Join online communities, attend workshops, and read research papers to stay updated. Continuous learning will keep your skills sharp and relevant. Next, let's look at how to apply data structures in your projects. Apply your knowledge of data structures by building projects, contributing to open source, or solving real-world problems. The more you use data structures in practical situations, the more confident you'll become. Experiment with different structures to see how they affect performance and usability. Next, let's discuss collaboration and teamwork in data structure projects. Working with others on data structure projects helps you learn new perspectives and techniques. Collaboration encourages knowledge sharing and problem solving. By discussing ideas and reviewing code together, you'll improve your understanding and write better software. Next, let's look at the role of documentation in data structures. Good documentation is essential when working with data structures. It helps others understand how your code works and makes maintenance easier. Always document the purpose, usage, and limitations of your data structures. Clear documentation leads to better collaboration and fewer errors. Next, let's discuss testing and debugging. Testing and debugging are crucial for ensuring your data structures work as intended. Write test cases for all operations and handle edge cases carefully. Debugging helps you find and fix errors early, leading to more reliable software. Next, let's look at optimizing data structures for performance. Optimization involves fine-tuning your data structures to achieve the best possible performance. This might mean choosing a different structure, reducing memory usage, or improving algorithms. Profiling tools can help you identify bottlenecks and areas for improvement. Next, let's discuss scalability in data structures. As your applications grow, scalability becomes important. Choose data structures that can handle increasing amounts of data without sacrificing performance. Consider how your structures will perform under heavy loads and plan for future growth. Next, let's wrap up our discussion on data structures. Congratulations on completing this journey through the concept of data structures. We've explored definitions, types, real-world applications, and best practices. Remember, mastering data structures is a continuous process that will serve you well in your programming career. Keep practicing, stay curious, and continue learning. Data structures are the foundation of efficient software, and your understanding of them will open up endless possibilities.